listen, Ken and okay, so we start. We are glad to have today with us Yehuda Afek from Tel Aviv University, and Yehuda, the talk will proceed like this. Yehuda has the fortune of having two mentors. In the area he is dabbling, he's doing great things in two areas, in distributed algorithms with me, and with networking with Len Kleinrock. So we will both each one of us knows well our facet, but he's multifaceted. So I will introduce Yehuda on my part, then Len will introduce on his part, then if time is left, the speaker will speak. And then we'll have question and answers, and hopefully no. Then we have a special guest. The talk of Yehuda is about DNS, domain DNS, domain network, what is this? What?
Domain name.
Okay, DNS, I know. So Yehuda found the flaw. We have the inventor. We have one of the really, networking pillars with us today, Paul Mockapetris, and he will hear what Yehuda claim is wrong, and then we now suspect that he knew about this fault, but I shouldn't say anything. And so after Yehuda finishes, Paul will take over and give his idea about what he heard, and then we'll go to, I will moderate questions and answers, and you don't have to write the question. Just if you do something on chat or raise your hand, I hope that I can enable participants to speak. So about Yehuda, I can start by telling you that I'm now feel like the old generation, so I'm the old generation, and every generation says to the new generation, you don't know how good it is for you. So in some aspects, I know that in some aspects it's not that good. So in some aspects it's very good because now I'm a chair and I'm negotiating his faculty, and I learned of something, for me it was completely new, something called startup package. So I can tell you that when I came to UCLA, there was no startup package, no nothing, okay? So I came to UCLA, and the PT of Len, he says, look, I have this new student, an Israeli like you, and he will work with you. We'll sort of share him. So I started to work with Yehuda, and it never stopped. I can just tell you that I started with work with Yehuda, and my neighbor across the wall, I don't remember who it was, asked me, why there is shouting? Are you beating each other? Why there is shouting going? And once in a while, the shouting involves idiot and chmor. What is chmor? I said, this is a donkey in Hebrew. What's going on with you? I said, this is how Israelis do research. Okay, and it continued. From there on, it continued like this, and it continued to the point that both our wives said, you are married to each other more than you are married to us. I don't know if this was a result of this. We have our problems, but there is also perhaps some envy in other directions. So just of the history of Yehuda until he came here, he did his PhD mainly in the area of distributed algorithms and went to work with somebody, Mike Merritt, and there was another guy. Also over there, he also did distributed algorithms and networking. Forgot the name of the guy. Yehuda, who's working with the guy, the networking guy in AT&T, a very famous name too.
Maximchuk.
Worked with Nick Maximchuk. Stayed in AT&T like 3 years, and then moved to Tel Aviv as professor. Since then, he's been a professor in Tel Aviv University, retiring this or next year. And In the meantime, he took a detour, took 3 years off, about 15 years ago, 20 years ago, of teaching and opened a company, Riverhead, which is my opinion, the only fault of Riverhead is it was ahead of its time. It was about denial of service, and eventually it was bought by AT&T for
Cisco.
From Cisco, sorry, from Cisco for, you know, in the realm of these things, when you are bought, it was bought for less than 100, so it's a little bit of a pittance, and they didn't pursue it, and the whole thing sort of collapsed. And now when he tells me, you see, this company is successful, the idea, this is part of our idea and stuff like this. So doubling up while I was with him in the Simon Institute in the fall, he tells me, you know, my student and a co-worker, which is also a colleague in the Interdisciplinary Institute, Disciplinary Center in Tel Aviv, which is now, you know, happened since yesterday, it was announced university that has a PhDs in computer science too. She's a professor there, so with his student and his former student, they discovered this flow, which is going to talk about. And now the other facet will be presented by Len.
Well, that was great, Ellie. I'm going to make mine a little shorter and leave some room for Yehuda's talk. But we didn't have any fights. When Yehuda and I worked together, he is and was a classy person, brilliant, creative, fun, and he's now not only my academic son, but a real family member to my wife and I. He's what's called a mensch in Hebrew. No, that's Yiddish. And working with him, you know, we got together because he was perhaps one of the most brilliant students in one of the hardest courses that was taught in computer science at the time, and excelled so much that we began to work together without yelling. We got creative.
That's why we didn't get far.
So, as you mentioned, he worked, you know, I've known Yehuda for almost 40 years, and he's never disappointed. He's always produced. And as an example, his PhD dissertation was entitled Distributed Algorithms for Unidirectional and Complete Networks. What wonderful words. Networks, algorithms, distributed. He laid claim early on to that domain, which has been his pursuit, his research life since then. A couple of years before that, wrote a paper in which the word routing was included in the title. Talked about computational overhead as well as performance. Talked even about an application to packet radio networks. So Yehuda was there early on working on these really critical problems, which continue to today. Now, the anecdote I'd like to say is the following. When he graduated in 1985, I helped him get a position at Bell Telephone Laboratories in Murray Hill, New Jersey. You don't get to a better place than that. That was the premier research organization of great historic fame and a wonderful place to be. 1 year later, Yehuda returned, unannounced, stuck his head into the side of my office, looked at me, and he said, "How could you do that to me?" He was talking about New Jersey, not about Bell Telephone Labs. New Jersey is not the best place in the world to have an exciting young life. Since then, we've continued to work together. We're working together now on some research and some practicality. His impact has been enormous. And today we're going to hear about his finding a new DNS vulnerability, which involves a devastating attack. And as Ellie mentioned, this solution is now being incorporated into the DNS software of places like Google, Microsoft, Cloudflare, Amazon, VeriSign, and many others. So Yehuda, please give us the story on your DNS system attacks and mitigation.
Well, thank you very much, Len and Ellie, I'm completely flashing from the introduction. I hope the audience not to believe everything that's said about me here. Anyhow, I will be talking about the DNS system and some attacks and the mitigations of these attacks. It's a joint work, as Eli mentioned, with Professor Anat Bremner-Bar and our joint PhD student, Lior Shafir. And let me start the outline. I will spend about 20 minutes, some introduction and previous attacks on the domain name system. We'll go over what it is, and then we'll talk about the new vulnerability that we discovered, mitigations, and the last slide, the conclusion, will be some philosophical or some takeouts from this experience. The attack actually was announced 2 weeks ago on May 19th, made some headlines on ZDNet, on Wired, on Fox News, and some more than 10,000 news items in the internet. What's the domain name system, the DNS? It's something that translates all the names. I'm just giving a basic introduction that you type into your browser. When you start Zoom, you go into your email, into an IP address, without which your device, your computer cannot find the information it needs to display for your resource. If the DNS doesn't work, the internet is useless. It's like, assume the whole world is covered with fog, all the signs are covered, street names are disappearing, GPS doesn't work, the roads are perfect, everybody can go on the road, but nobody can drive, nobody see where he goes, what he's going to, and the whole world is shut down. It's used, the DNS is very important because sites and the information is changing its IP all the time because it's hosted on the cloud for load balancing, for denial of service protection, for content distribution networks. There are various reasons for the domain name system to be so dynamic and being continuously updated. It was actually invented by Paul Mockapetris, that we have really the honor. I'm really honored for his presence in this talk. In 1987, it's an amazing system. I would say it even if Paul is not here. It's a distributed hierarchical system. Today it has hundreds, maybe 1 million servers working hierarchically, globally around the world, servicing billions of clients, millions of requests per second. We see two types of servers in the system. There are recursive resolvers, and there are authoritative servers, which are divided hierarchically into levels of hierarchy of servers. We'll see them in a minute. Let me just go quickly through an example and just how it basically works. When I'm in Tel Aviv and I want to visit the computer science page in Los Angeles, UCLA, I send a request to a resolver, a recursive resolver, probably in Tel Aviv, provided by my university or by my ISP. It's not in the cache. This is the cache of the server. So the guy, which is my representative on the internet, is going and doing the job of translating this into the IP address for me. It's asking the root. It has the IP address of the internet address of the root hardwired into the application. What's the translation of this domain name into IP address? And the root responds usually with a delegation. It says, go and ask that server. It's probably closer to the answer. He might be able to provide you the answer. This resolver asks the tld.edu. It's a top-level domain authoritative name server. He tells me, go and ask the UCLA name server, which is the authoritative name server for all the domains under ucla.edu. The server goes and asks that one. It gets the final answer. Final answer goes to the client, and I can go and visit Len's page, Ellie's page, and so forth. So we had one packet, one request, generated about 3 outgoing packets and 3 incoming packets into the resolver. We should remember those 3 incoming and outgoing messages. So as Paul already wrote in 1987, The requirement should be 24/7, highly available. If some servers crash, it still should provide the service. Should be quick response, because any latency is part of the latency for the response until we see the resource. The internet is for videos and information, not for address translation, so there should be low communication cost. The addresses of different resources keep changing all the time. New resources coming in, go out, millions of requests per second. It supports today even denial of service protection. We should make sure it's authenticated, that we know that the IP address we get is actually the IP address of the resource we want. And these are some property. It supports redundancy, stateless as much as possible, uses caching extensively to make the communication efficient. As we said, distributed, hierarchical, and open for everybody. So I will go now through 4 techniques of attacks that are kind of a building blocks in the new vulnerability that we observed. The first one is a simple spoofed DNS request flood. Since the DNS packets are usually over UDP, with a stateless communication, it's very easy to spoof. You can send a request to a server, pretending to come with one IP address, but actually you are coming from a different IP address. The server makes the request, get a reply, but you send many, many messages, hopefully saturating the recursive. That's one of the first attacks on the DNS system. And actually we had luck when we had our startup protecting from denial of service. We made a new patent of how to anti-spoof and authenticate UDP DNS requests by falling back to the TCP domain. Won't go into the details of the technique, but it authenticates the end user, make sure it's really the correct IP address that makes the request. Next attack, they use the DNS recursive resolvers as huge reflectors and amplifications. The hackers, the bad guys, learn how to issue requests which are small packets, generating large responses. And the request comes from the bad guy, but he spoofs the IP address of the victim. So the resolver thinks that he replied to the guy who makes the question, but it goes to the victim, saturates it with many packets of large size, so it's a reflection through the recursive resolver, and amplification. So we mitigate this also with our scrubber, which the first denial of service scrubber that we built 20 years ago, and managed to filter this kind of attacks with all kinds of heavy hitters algorithms. Next, the attackers try to reach the authoritative. They say they didn't try to take down ucla.edu, but they did try and keep trying to take down authoritative servers like Sony, a gaming company, and other CNN and government websites which are of a high profile. In order to do that, they send requests to the recursive, asking questions about UCLA or whoever the victim, hoping the victim to be saturated with packets. And this has been mitigated by the caches helping here. Again, heavy hitters and the same scrubber we had before. The attackers noticed that in order to make this attack successful, they actually better make random subdomains, prefix of the domain when they attack. So the cache won't save the victim. All the requests look different. There are billions of different requests arriving from a huge botnet. It could be a million participants in the botnet, as we'll see in a second, and all reach the victim. This time it's the gaming company, which was taken down in 2016 by this type of an attack. Again, we developed a method to protect this by a paper that uses distinct heavy hitters, which uses sophisticated sketches for online streaming algorithm to detect which domain gets many different subdomains which are illegal. This attack was actually used, was the largest denial of service attack that was ever observed, reached nearly 2 terabytes per second. This was the first one, was 1 terabyte per second. It knocked down DIN, a huge DNS provider. Several sites have been unavailable for several hours. Many routers in Germany were knocked down. In Tel Aviv, in Israel, many routers and DNS servers knocked down. You can see on the map all the distribution of the botnet. Those are all thousands, each purple circle are thousands of bots, and the other circles are hundreds and the tens of bots around the world. These are the attack surface, and the victims, those areas in the United States have been affected and couldn't reach PayPal, Amazon, Twitter, and so forth. All of this happened on 21st of October 2016. And we developed a reverse scrubbing to prevent from zombies to get into the IoT devices, but it's a topic for another talk. And before I present the new vulnerability, first of all, I should stop for one second. Are there any questions? Anybody wants to ask any question before I continue?
Yehuda, I will represent those that don't know anything, which I am one of them. And if you can translate to me the word spoof.
Spoofed is somebody who masquerade sends an IP packet with the wrong source IP address. I'm coming with IP address 123, but I put an IP address 5678. So when you want to send back to me, you will send back to the wrong IP address because you don't know where I'm coming from. Spoofed means that the source IP is not the correct IP address. It's not where the packet is actually coming from. And in the reflection attack, it caused the reflectors to send the replies to the victim and not to the place, the one who made the request. Okay. Rich, do you want to ask a question?
Let me see, you are not a host. Let me see if I can enable him.
If not, I will continue.
I don't see anything. How do you know it's Rich? I know
who was in charge of the Mirai attack? Actually, we don't know. That's a good question. Nobody knows who was in charge of the Mirai attack. It's a huge botnet, millions of bots, zombies. The code is available, and since then there have been other generations of the Mirai attack. But what you will see now in a few slides is something almost 1,000 times larger attack than the Mirai attack. So it's a devastating vulnerability that has been, okay, let me just talk about a few more properties of the DNS. Actually, those properties and designs have been already in place since 1987 by Paul, which is really an amazing, beautiful system. No blockchain, no cryptography, something that works for almost 40 something years, provide service to billions, amazing system. So we saw before how we resolved the IP address of the computer science department at UCLA. But what if the authoritative server for UCLA is down? And Paul was thought about it and said, when you get a reply from the higher level, one level above the UCLA name server, he will give me several names. So it will be backup servers, and each zone file containing the replies should be backed up in several servers. Like UCLA could back up its information at USC, at ISI, and at Getty, for example. So when you get a reply to my resolver here in Tel Aviv, he will send to UCLA, no reply in 1 second, timeout, go and ask USC, and go and ask ISI or Getty to get a reply. One of them will provide the reply, and you will have you can go on. That ensures high availability. Same thing happens between the top level, the root level, and the top level domains, or if there are more levels, it's not strictly only 3, there could be more levels in the hierarchy. Here also, you can ask either one of several servers in the top level in the hierarchy. So that's one thing. But if you look at this slide, actually something is missing here. Anybody can think, what is missing here? What is actually missing here? What's the problem here? But we are back to square one. The answers here provide me the domain name for the name servers I should ask. It doesn't give me the IP address. But how do I know what's the IP address of UCLA, of the name server of UCLA or at ISI? Well, Paul was actually, I think, working in 1987 when he invented the DNS system. Well, for that, we have to look more under the microscope or more closely onto the packets exchange. When they say the TLD level, the top level domain authoritative name server replies, he says, you can ask, go and ask, I redirect you to ask one of these name servers. He could either give me the IP addresses in a glue record, but many times glue records are not included. And I go and, let me go back. The recursive now starts a new resolution. What's the IP address for those name servers? It's a whole new, 4 new resolutions. And he gets 4 replies. Go and ask of referrals. Those replies are called referral responses. Go and ask either of these name servers, NS1 to NS4, at UCLA.edu, and here are their IP addresses. And so those IP addresses are, the exchange continues. You see each name with here, the reply says this is a name server name, and those are glue records. Since then, I don't know how it was in 1997, but already then, Paul noticed that the glue records are very tricky. He introduced them, I believe, in order to avoid infinite loops, that you go back to the same guy who would tell you back to the same guy to get his IP address, so they just give you the IP address. But hackers and bad guys have used it in order to hijack different domains and implant IP addresses that you are not intended. So many times, the name servers, the recursive name servers, don't trust the glue records and go and try to figure out the IP address for these domains on their own. Here is a real example. This is from a real reply that we asked for Microsoft.com. And you see, you get about nearly 70 packets, 70 requests exchange just to figure out the IP address of Microsoft when the cache is empty. So in theory, it was 3 packets, as we saw a few slides ago, but in practice, it's much more like 70 packets. So that's one issue which is not new. Everybody knows it. But we use this and the previous techniques I showed you. And here I will show you the first attack variation, the non-existing name server attack. On the, here I will use the top level domain. I want to attack a top level domain authoritative server. The attacker in our attack is a sophisticated one, but it's very simple to obtain, as I will show you later. He has a zombie, as we saw before, in different IoT devices or on kind of devices that has the client of the attacker. But the attacker also owns or controls an authoritative name server, which we call here attacker.com. The attacker issues a request to a honest resolver. Please translate the domain name attacker.com with some random string here, so the cache is ineffective. And the resolver says, attacker.com. He already resolved attacker.com within the cache. He knows the IP address of the authoritative. And they ask him, what's the translation? And this guy responds with a referral response. But the DNS, we are testing the bind DNS, which is the most popular software for the DNS system today, has no bound on the number of referrals that you can put in a referral message. the maximum that we could pack into one UDP packet are 135 referrals for different name servers. The attacker says, go and ask one of these 135 name servers. So the recursive issues now 135 resolutions for different domains, are domains of name servers, of authoritative name server. But the attacker has crafted the packet very carefully and used here fake domain names. So nothing is in the cache. They are never cached because each time there will be different names. And since they are here on the second field of the domain, it's the field of the top level domain. So it goes and asks the .NET authoritative name server, what are the IP addresses for all of these strange names? The response would be, of course, non-existent, NX name server, but the response is not so important for us. The number of packets here is what is important, and using the random fake names, so the cache doesn't help here. And in this case, we get an amplification factor of 135 requests that are sent out of here. Actually, the DNS is these days is working twice as much. Each response is once for IP version 4 IP address and another request to resolve it for the IP version 6 IP address. So there are 270 requests in here, times all of them fall back to TCP because there are too big question and they're using DNS security most of the times. And it ends up to be a amplification factor in the number of packets. Actually, the number of packets for one response is over, it's a 3,200. But we divide it by 2 because the attacker issued here 1 packet and 1 packet. So it's over 2 the cost of the attacker. So the amplification is 1,620 packets amplification factor. And of course, like in the Mirai attack, you have a whole army of zombies. You have a botnet, a huge botnet that provides this attack, all coming with different requests. The attack is now amplified by this number, and you get a tsunami of packets on the top level domain. This was just a simple attack. We'll see a few more in the next few slides. Any questions until here, or is something not clear?
Yeah, why it is simple if the attacker needs to get his hand on, or her hand on a top level domain, or the top level resolver, it's not resolver, or the top level.
No, Eli, the attacker here, this is not a top level domain. It's true, I drew it at the top of the page, but
how
this
the resolver is spoofed or get crazy to talk to you guys over there with the
attacker.com, the authoritative name server attacker.com is a real one, and there's an IP address. It's recorded at all the levels of the directory automatically. There are billions of domains like this that are registered. And I will show in a few slides how I do it. It's really trivial. It takes you 2 minutes and you have a authoritative name server under your control.
I see, okay. So you say why this is simple. So you didn't explain why this is simple to do this attacker.com that will send me back 135 names.
It sends 1 packet. It sends 1 packet, but it packed into this 1 packet names of name servers, 135 names of name servers. It's 1 packet.
But this is not a normal behavior of the attacker of authority.
It's normal. It's completely legal. It's accepted by Bind, and actually Bind acknowledged that you can do it and it works. We actually did it. So we mounted this attack on the internet and it works.
If it's a normal behavior, why did you put the red bad guy on top of him?
Because the attacker crafted normally the authoritative don't fake random names which don't exist. There is no name server ns1 fake1.net.
So how did the attacker get that this guy will do something like this?
The attacker controls this authoritative. He has the zone file, and he crafts the packets. He can put into the response whatever.
Okay. So the attacker, it's not that simple. The attacker has to control an authoritative computer.
Exactly, right?
Okay.
And this is very easy, as I will show you.
This is easy, okay.
Yeah, everybody acknowledge this is a trivial thing to do. So we did this attack on a TLD, but next we want to attack a second level domain, like a Sony or UCLA this is a top level domain, this is a second level domain, SLD. How do we do it? Pretty similar, but there are some restrictions here. Now we send the attacker crafts a message with only 37, I will explain in a minute why 37 name servers. And now the random name is on the third field of the domain because UCLA is the victim. 37 because bind has a counter which says I will not issue more than 74 extra requests for one question I'm receiving. For one original request, I'm allowing at most 75 different requests. One request was expanded to go to the attacker. We have 74 more, but each one here will be twice because one for IP version 4, one for IP version 6. So only more than 37 won't help here, will only fail the whole process. So here there are 74 requests, one for each of, two for each of these, IP version 4 and IP version 6. And you multiply it, my screen doesn't show everything because of the Zoom things. And the amplification factor here is 74 because of this 37. And again, I will use a huge zombie net in order, a botnet, to attack both the recursive resolver and the UCLA, the second level domain authoritative server, will be shut down due to being overwhelmed with huge amounts of requests that they need to process. And actually we did it, and it did knock down the servers in our lab. Any questions right now? Yoni, Eli, they don't know how to be unmuted.
I just dismissed my question and answer.
Thank you. Can you hear me?
Yes.
I was wondering, how is this different? Sorry, I'm a beginner here, but how is this different from the first attack? So now we're using fewer numbers, 37, but how does this attack not the TLD domains, but rather the UCLA domain?
There are two questions you ask. It's because here you see the random number, the fake random number is on the third field, that keeping the UCLA EDU part of the name server name in the crafted packet of the attacker. And the 37, it's a good question. I didn't mention it. If you go back here, when we did the attack on the TLD, bind doesn't count requests you make to the root or to the TLD for one request. So it lets you ask as many questions as you want to TLDs or root servers, but when you go down to second level domains, it does count. So any lower level command, it restricts to at most 74 additional requests.
Got it, thank you.
No, good question. So I won't go into the details, but you can do the same thing, but you can craft, the attacker can craft the responses in a smart way. So there will be multiple resolvers that will attack one second level domain authoritative name server. And it will definitely take this one under the water. All its backups will be shut down. You can do the same thing to put all your fire on one top level domain like .com, and you can disable, you can have huge amounts of traffic. Although the .com is a very critical structure, it by itself hundreds of servers all over the world with Anycast and different load balancing techniques. Still, we can mount multi-terabytes, like huge amounts of traffic on the .com to swamp it and take it down. You could do just to take a specific resolver. Now the botnet has to be a local one. All the LA area or Southern California would go to the same recursive resolver, say of AT&T or of UCLA, and they will swamp that resolver or the Cloudflare or Google resolver and mount the attack, craft the packets here in such a way that the attack will go to different authoritative name servers. So those are all variations of the attack. And the last variation that I will again explain in a little bit more details is where we do it recursively, but we can do it only twice, one recursion, so it's actually taking the attack square. Attacker again issues a request, sends it to the attacker, but look here, the attacker response is now the attacker as if he's attacking itself. The attacker sends back a response, ask me for the resolution of these 37 name servers names. NS1, attacker.com, NS2, attacker.com. So what will the recursive resolver do? It asks the attacker, give me the resolution for this IP address, for these name servers names. 74 questions. Now the attacker has the credit, he has the to ask 74 more referral responses. So it sends now 74 responses with 135, the maximum number of name server names in the referral response. And this by itself will now make the resolver making 74 times 135 requests. When we did it on real servers, the server couldn't, just for one request, the server was knocked down. It couldn't sustain the number of requests because he has to issue all of these requests at once. You see, the referral response has two, as Paul invented them, has two purposes. One's for redundancy, so you can reach the backups, but also you need to resolve all the names immediately so they know which one is a slower, faster response, has lower latency, and should be used for further requests. So the implementers of the DNS software issues all the requests immediately at once. So that took the bind resolver under the water immediately. And just imagine, now I can do it on the root. That's why there is no counter, because as we said, the software doesn't count requests made to higher level authoritative name servers. I can swamp the root name servers with a gigantic amount of traffic. Just from one request, I get 250,000 packets. And the amplification factor is over 3,000. And just imagine if I do it with multiple botnets all around the world, and we're using several recursive resolvers, and I can easily, as I will show and explain to Eli in a minute, have several authoritative name servers on my disposal that I control. I can take down, or you know, we never tried it, and I don't know how. I suspect it would take down, will use a huge damage to the DNS system. Any questions at this point? Any additional questions, please? I don't see any more questions. Okay. So I assume so those are you can have other variations of this NX non-existing name server names, because the responses here are non-existing, the response of the authorities, when they're still able to respond. As Eli asked, there are two ways you can acquire, the attacker can acquire and control an authoritative name server. It costs about $1 to get a new domain, It takes you a few minutes to acquire one, and you can have it associated with any authoritative name server hosted by a Rackspace, by VeriSign, by Cloudflare, or by any other, or your own server. It's very easy. We did it for our experiment several times. Actually, Lior was the one who did amazing work implementing and testing all those attacks. And if you don't want to acquire one, the hackers have many automatic techniques to break into authoritative name servers, hijack them, gain the operator's credentials, and control the authoritative name servers. We tried open resolvers all over the world, and you can see they got the amplification factors and number of packets they have to process for one request. We didn't take them down. We only issued one request, and we see here on the middle column how many packets each of them had to process for one request, including Cloudflare, Dean, the Google, and level 3. And you see here the full list of name servers providers, DNS providers that we tested, and they all suffered the same flaw. Actually, there was somebody about 5 years ago, he almost noticed the flaw, but he didn't quite do. He did see that the glueless referral responses could be used, but he mounted an attack where the attacker sends back to itself, and he achieved a 10 times amplification factor with the glueless referral responses. And Paul is actually cited for mentioning already in 1987 that people should watch out for the possibility that there will be too much work done to process just one request. And maybe Paul will be able to tell us more about it. Of course, being part of the light, not the darkness of the internet, but the light part of the internet, we look immediately for mitigation. Vendors are using all kinds of counters, but those are double-edged sword. Once you have a counter, it's easy for the attacker to make sure the counter hits the threshold, and then it becomes by itself a denial of service. So our suggestion, we have two suggestions: max fetch. What we claim is once you get a referral response with a number of name server names, you don't need to resolve all of them at once. To resolve only one per request you get. If you don't get a response, resolve one more. For each request, resolve one more name server, one by one, so you amortize it over all the requests for that domain until you resolve all the name server names. And actually, most of the vendors and the providers have used our techniques to solve the problem, to patch their software. And we also suggest to limit the number of name server names you can pack into a referral response. There is no reason to put 135. Nobody is using this large number. Actually, as you can see here, most of the requests we measured on the internet, they use 2 name server names in a referral response. Only 1% is using more than 7 name servers in the referral response, and only 0.01% is using more than 13 name server names in a referral response. We believe 5 or 7 name server names is the maximum that should be allowed. So if you do the attack again, here you can pack only 5 with our new restriction of the max breadth, and the response will be just 1 packet because of the max fetch. And if the zombie is attacking, each packet will generate just 1 packet from the resolver, so the application factor is much more normal. It's about 1 request to 1 request. And if you consider the TCP packet, there are a few more packets.
But you say that max fetch is for efficiency, that I will find the first one that answers, and from there on we'll talk with him. So you are using it.
No. When I get a first request, I resolve only the first name server name. I get another request for the same domain, I will resolve the second name server in the same record in the same list of name server names.
No,
Each time I get an original request, I resolve one more. I didn't go into it. All the software, they use all kind of estimations of the latencies of the different name servers to try and ask usually the one who provides the least latency.
So you lose this. You lose this, the one that
No, I
provides
don't
the...
lose it. I just
Why?
do amortize it. I don't lose it. I just amortize it. There's no reason to do it all on the first request. Actually, I will show the latency in the next slide. Here you see that actually the amplification factor is down to 3 from the 75 we had it in the variant where the amplification factor was 74, not 75. And it went down to 3 in our experiments. The latency, we didn't notice any failures because of this. We didn't, in our experiment, doesn't say that it doesn't happen. We didn't notice any case where a resource could not have been found because of this max fetch. And here you don't see anything in the graph because the two, the original bind and the one with the max one, have the same latency as far as you can see on these graphs, both two different data sets or experiments. And we take only the 1%, I'll detect the 1% slowest responses, and we see the difference between bind and the bind with the max one fetch. And you see they are about the same. Sometimes even the max one fetches have a better response time. So if anything, sometimes it behaves better because it's much fewer packets and the load is smaller. After discovering this, the whole world, Steve Crocker has given me an article a few hours ago with about the fight between the good guys and the bad guys on the internet. So this is part of the war between the dark side and the light side. And being on the light side, we did a responsible disclosure. We contacted about 20 companies, both vendors of DNS softwares and providers of DNS services, told them about the problem and gave them 90 days until May 19, which was 2 weeks ago, to patch the vulnerability. And they all responded and cooperated, and we worked together to patch it. And they asked us to test, and Leo tested their patches, and some of them had to do tests again and again until they got it right. And following this, you see the 4 major vendors, they all issued the CVE, which is a report of a patch. And the providers, they've all patched their software and to fix it so it works okay now when the vulnerability became public. So now to the interesting part. It's pretty worrisome, there is this internet is a very critical thing that we use. It's like for phone calls, for classes, and there's a fatal flaw. Is there another fatal flaw? This attack is 800 times, at least 800 times larger than the Mirai attack. The Mirai knocked down for many hours critical services. What happened if this attack would have been mounted? Maybe, something has moved. This line should be over the sun. It's very worry. It's not worrisome. It's a very worry. Is there another flaw? Maybe we should look for an automatic way to find those flaws, like program verification, formal methods. We should take all the BGP, the DNS protocols and make sure we didn't miss any flaw. Like we were using this airplane, the internet, but there is a flaw. The airplane could have crashed we didn't know about it. What we can see that the vulnerabilities are a trade-off of availability because this referral message was introduced by Paul for higher availability and quick response times. You can choose the name server with the fastest response, but that introduced the vulnerability. And as we discussed before, counters are not such a good idea. DNSSEC by itself doesn't provide any remedy here, but there is some aspect of DNSSEC which called NSEC. I won't go into the details. I don't know how much time we have. That helps a little bit to alleviate the problem. We could think of other approaches. We have all kinds of ideas we are researching these days. Any more? This is the link to our website where we report the vulnerability. I'll go back one slide or stay on this one. Are there any questions, or Eli?
Yeah, I still don't see, or I missed it. Why it's easy to get your hands on authoritative server? You know, the one that has the.
Because it's easy. It's easy because it's really
easy. So let's not.
No, because
let's do it not easy.
Eli, you're a good guy. That's why you don't understand why is it so easy to do something bad. But the bad guys, they know easily. You can. It took us. You know, we spent $1. We got a new domain.
Oh, I see. This is the way that you do it. Okay, this is the option one. Is the way that you get control by putting a domain.
You buy a domain. Now you can buy a domain attack.
I missed it.
For $1. It takes you a few minutes. It's hosted on some server on the internet by VeriSign or by Dean or by somebody. And you have it. And you control the zone file. You can control what are the responses that your domain, authoritative domain replies when it gets questions. It's under your control. And you can also break in to a legitimate authoritative name servers. The bad guys doing it all the time. And,
Got you. Okay, so this is, as I said, we will first go to Paul to sort of get his reaction to this, and then we'll go to question and answers. So in introduction to Paul, you know, you still, when we talked about you giving this talk, I say that my main question in talks is, when you come with something new, with some observation, I don't believe that the world before you was stupid. So if you can verbalize what is the things that you saw that other missed. Now you did it so simple that it looks like how all these people, smart people all over the world missed it, and especially how our smart Paul missed it. So you didn't sort of illuminate, look, what they missed was this point, to pinpoint what did they miss? Why did this was not visible to them? So perhaps Paul can, with his reaction, also refer to this. How come suddenly, which refer to, how do we know that there is no other fatal flaw? So Paul, it's the floor is yours.
Sure. You know, the people are always talking about security flaws in the DNS.
Paul, can you put your video on, because you can put your video on?
Sorry, I couldn't get my, like I said, I couldn't get.
Oh, you don't have a camera. Okay.
Yeah. I have a camera, but I had to run it a virtual machine with Windows in order to get connected. I don't know why. At any rate, there's like the famous Dan Kaminsky attack and so forth that showed flaws in the original DNS security, which I would argue there actually was no original DNS security. So that, you know, it was a door that didn't have a lock, or maybe the door, there was no door in the doorway. I mean, it was built in a friendlier time, and security was by design not part of it. I mean, it's not like it was an accident and it was left out. This, the simplest way that I explain it is the Wright brothers did not have a drink cart nor a bathroom in their first airplane. And these things have evolved a lot since then. The first time that I saw an attack of this nature, it was actually a misconfiguration when Rockwell was bought by Boeing, or when companies merge these DNS servers, it's possible to create a configuration a little bit like it. Now, you've weaponized it and refined it to a degree that surprises me somewhat, but this has always been there, and that's why I had suggested in the implementation guide that you ought to make sure that there's a finite amount of work that you perform for any particular request that's incoming. And that was both because some of the algorithms are tricky, and so you want to just avoid any possibility of having an infinite loop in your server, but also to tamp this kind of stuff down. So, you know, it's an interesting refinement of, you know, a possibility that always was there. I mean, people have always been looking at various algorithms about what's the best way to search. You know, I mean, you could say, well, gee, if what you want to do is to have the, you know, maximum performance on your DNS server, that whenever you have a name that you might want to go to, a name server that you might want to go to, you should immediately try and resolve it. And that would play into the hands of the attacker here. But it also means that your response is not as nice as it would be for good guys. I don't know what to say about that. I mean, I think that's a trade-off that was always recognized, but, you know, hats off for you for this new amplification.
Eli, it's the same way. You have a problem in theoretical computer science, and all of a sudden you find a very simple solution, and you say, "Gee, how come for 20 years I didn't come up with this simple solution?"
I found few simple solutions in my life, and I always was able to pinpoint what others didn't see. So that's my. So Paul, thank you very much for. Elaine wants to say something. Yes.
So just going back to those early days of a different environment, as Paul pointed out, was a friendlier environment. I'm noticing that there's two ways to annoy the system. One is to drown it, and that's what we're talking about today. A denial of service attack drowns the people you want to kill. The other way is to choke them, so they can't do anything, you know. And we started out by choking. We started out by having all kinds of flow control, which constrained how much traffic could exist between endpoints and internal points. And I find it interesting, those are different kinds of ways to either manage or abuse flow. It's just a philosophical point, not a technical point.
Yeah, this reminds me a little bit of The Godfather, you know, where he talks about every time I try to get out, they drag me back in. Well, I think every time you try and build a perfect world that's datagram oriented and stateless, all of a sudden they start dragging you back in by allocating resources on a particular path. One of the things we did in the original code was to have flow control both on an address basis and on a name basis, so that the number of outstanding requests you would have to a particular IP address was limited in order to avoid some of these problems. I don't know whether or not the Vine people had any such notion, but that was in the original code that ran on the DEC 20. We just kind of avoided overflowing a particular IP address. I mean, one of my questions is there any way to make the world safe for datagrams? Because they're just kind of like, they seem to be inherently datagram services. They seem to inherently have this possibility of being very useful for DDoS attacks.
Yeah, because it's easy to spoof them. Well, if we redesign the internet, I don't know.
I know we have another internet personality with us, our Professor Lisha, and she's working on data networks. And I wonder if this applies also to what you have in your mind as NDNs that you are working on. Is Lisa still with us here? Yeah. I cannot talk, but if I see you try to talk or do something, I'll see you at the top, and then I can enable you to talk.
Yeah.
You see Alicia? Okay, so enable her to talk.
Here, I allow to talk, but I...
Alicia Zag, yeah, you can allow her to talk. Yeah, Lisa, you can talk. Talking permitted. Yeah.
You can hear me, that's great. So the named data networking is also a datagram design. and that it does not suffer from this problem. I just say that.
I didn't hear. It also suffers or doesn't suffer from this problem?
It's immune.
It doesn't suffer.
It's immune to this problem by design.
Immune, that's a good word today, to these days. Yeah, we all want immune. Okay, thanks, Lisha. And any other questions? So do press a chat or press something which will lead you to the top, and then we can enable you to talk. Any other questions?
I think Paul Eggert is asking, and
Paul Eggert can talk. Paul Eggert, talking permitted. Paul, you want to ask something?
Yes, there was work done in like 10 or 15 years ago on doing denial of service sort of formal modeling. You know, I'm thinking of model checkers like MOD and that sort of thing, where they attempted to do this with some simple protocols. Has anybody tried to do that to something like DNS, which is more complicated than the ones they were looking at? Like I'm thinking like SIP, which is the VoIP initiation protocol, had a similar issue.
Paul, let me, before I move it to Yehuda, you are asking about verification. As far as I know, I was involved a little bit in verification, and verification is about, here is a program, does it work? The verifications that we talk here has to do with somebody attack. So how do you know that you looked at all the possibilities of attack? This is a verification, security verification. There are people working on it, but I don't think that this is area which is ready to prime time, because we don't know how to model to capture all the possible attacks. So I think this is I don't think verification is the answer, because it has to do, how do we know? I didn't know that you can get your hands on authoritative by doing a simple domain name. So.
Well, Eli, I must disagree with you. I think
that's good.
There should be a way for verification and formal method. Actually, the thing I hope to do is to take it to Muli Sagiv, who is next door to me here in Tel Aviv, and to think how we can actually try to find other flaws or to verify that it's true. It's much more complicated. It's a distributed system. To your previous question, Eli, the attack is a little bit more sophisticated. We use the previous attack techniques of spoofing, of using random names, and the attacker has to control two entities. He controls both the client and an authoritative. So there's some sophistication in the attack that attacker didn't, or not that we know, have a tricky way of mounting the attacks.
So what you say is the space of attacks is so big that it's really hard. It reminds me, if Jens is in, Jens had a visitor from ETH, that this is his life is verification of security. And I asked him this question, and he has some answer, which at the time I remember only that I remarked myself that it's not satisfactory. How do you do verification of security protocols? So is Jens there? No, I don't think so. Okay.
This is not my area, but I wonder if there's a theory behind taking the whole space of attacks and grouping them. So if you handle one aspect of it, you prune an entire portion of the tree, you've taken care of those. I mean, we seem to be in a state where we're ad hoc finding these kinds of flaws. But if somebody characterized the space in a formal way and identified classifications and groupings, so you can say, make one statement and handle many at the same time.
Not that I know of, but we do have Jens, we do have Jens with us, and perhaps Jens is doubling up in verification, but perhaps he can voice some opinion here. Jens, you can talk.
Oh, thank you. I think it's a wonderful idea, and doing work with Muli Sagiv is likely to be productive. And here at UCLA, we have Todd Milstein, who's doing verification of networks. So he's another possible collaborator.
Yep.
Yeah. Okay. I don't see the George.
Hi, Professor.
Connected to it. Okay. Any other questions?
Hi, Professor.
Before we,
I'm,
yeah. Any other?
I'm
Yeah.
PhD student with George Verghese and Todd Milstein. And we recently made a paper submission and got accepted for SICOM, where we started a formal method for DNS. So we formalize DNS to some extent and show how we can do proactive verification of DNS configurations. And we don't talk with respect to the attack and stuff. We just try to figure out, like, given the set of zone files, is there any query that can lead to a bad behavior?
I don't hear you.
Who is talking? I don't even know who is talking.
Siva.
Siva. Okay, Siva. I see you. Okay. So you vanished for a while. Can you repeat the question?
Oh, hi. Can you hear me now?
Yeah. But try to keep it like this.
Okay. I'm a PhD student with George Verghese and Todd Milstein. And we recently written a work formalizing DNS, and we show how we developed a formal model for DNS and used it for proactive verification of DNS configurations.
Yeah, but the question that we are talking about is not verifying the DNS configuration or stuff like this, but verifying attacks.
Yes. So the attacks is in the other domain. So we started with saying that, okay, given the configurations, is there any bad input to the configurations that can lead to a bad behavior?
I see. Okay.
A configuration of one machine or the whole distributed interaction between different servers?
It's an offline kind of simulation based, like it's similar to static analysis. So you take the config zone files from each of the distributed ones and try to simulate a behavior, saying that, is there any possible input query to this configurations that can lead to a, let's say, black holing or something like that?
Mm-hmm. Maybe you can show the paper with me.
Yeah.
Okay. George knows the address of Yehuda. Okay. Any other questions, comment, or anything like this? So let me do. I don't see any.
One comment.
Yes.
That was a great presentation, Yehuda. Congratulations.
Thank you so much. Thank you.
I will. He took the comment out of my mouth.
Sorry.
But
I have a question about Kaminsky reported that 6 months after he disclosed his flaw, there was still like 20 or 30% of DNS servers were still vulnerable. Can you contrast his experience to yours? Because it looks like you're getting better response from people doing servers.
Well, yeah, we were in contact with all these companies that you see on the slide, and they all responded very, showed a lot of responsibility, and they gave them 90 days. And they asked me to explicitly mention that they've patched their software. So all of them.
So don't try to spoof them.
You can try, but it will not work. At least so they claim.
So the industry's gotten better since then.
I hope so. Those are not everybody, I must say, but everybody that I know, there are few that are not here because they were late into the game. They are also either patched or have patched. It certainly covers more than 95% of the market, but I don't know.
This is Paul Mockapetris. I guess it's a positive aspect to the centralization of the DNS that's going on these days with DOE and so forth. I guess that means it's easier to patch when things are centralized. Although it still makes me a little bit queasy.
Yeah.
I bet you can find lots of open recursives though that aren't patched.
Yeah. Well, we opened a Slack channel with all the vendors and the providers, so we will actually use the internet to communicate and discuss the patching.
Yeah, but there's all these people who are going to be running old versions of Bind or God knows what.
Yep.
Okay, so before I say thank you to Yehuda, I want to plug in we have two 201 today, this week. And all of them are networking, and all of them are by our former PhDs. So on Thursday, we will have the founders of 1000 Eyes that was recently bought by Cisco also. but this one is a unicorn. And because they are unicorn, they will not, they will get land by himself, not shared with a lesser like me. And Len will moderate, and they will present what was their idea. They will present the company, and then Len will go with them through questions and answer, and then the audience answers. So please show up also Thursday at 4 o'clock. And I want to thank Yehuda. You should know that for Yehuda, it's probably close to 3:30 a.m. in the morning. So, yes, close to 3:30 in the morning. So really, this was, we really thank you very much. And Yehuda was supposed to talk on Thursday, and I twisted his hand to move it forward. So also thank you for taking the twisting of hand without shouting too much. And
thank you very much for everybody for the attention. And
it was very nice talk. Thank you very much, Yehuda. Very nice. We are proud of you.
Yes.
Thank you so much.
Yes.
I'm blushing. How do you say? Yeah.
Blushing.
Bye-bye.
Absolutely.
Bye.